So hello everyone, my name is Mayank Shrivastava and this is group 13 and this is a video demonstration for EE542 Lab 5 fast reliable file transfer with custom TCP IP network. So what is the objective? The objective of this lab is to investigate and enhance the performance of TCP in scenario involving lossy link by kernel level modification. So basically we are doing a kernel level modification in this and increasing the performance of TCP. So this is basically a simple background between TCP and UDP. So TCP is more of a connection-oriented, reliable network mainly used in web browsing, file transfer, and email. And UDP is connectionless, and there is no guarantee of packet delivery. And this is mainly used in streaming, online gaming, etc. So challenges for TCP: congestion caused by network overload leading to packet loss, and there's also loss of unreliable network caused by packet loss due to inference and not and congestion. So this is a procedure of building kernel. So first we are going to install git and do some initial setup. So after that we'll clone version 5.4 this kernel from GitHub and then do some internal code changes which I'll explain, and later on Vikram will explain it in more clarity. And then we will install some library for building the kernel. After that we will do a incremental build in the custom kernel and then some grub modification. So this is a image for our custom build in our local Linux environment, and this is the file transfer before the change of kernel. So you can see it is showing bandwidth of 10.6 megabit per second. Then this is a simple network interface of our router. Then this is a ping test between server and client after the changing of client. So you can see the RTT increased, and this is the file transfer from server to client in local Linux environment after the changing of kernel. So you can see it drastically decreased the bandwidth. This is a successful modification of kernel. Then grub modification. Now TCP performance gradually decreases in lossy time with increase in drop rate. So summary, and now I'll explain you some of the codes. So this is a code for TCP input. So the first change we did was uh, to directly link it to max quick, and the next changes we did that this is the next change. We commented out the other line, and then instead of giving a right bit shift to a window, we gave this value. Then instead of sending the minimum value, we directly send the window clamp value. Then in over here also, instead of sending minimum value between window clamp and RCS thread, we directly send the window clamp. Then over here we also directly send the window clamp, control clamp. And this is the last change we did in input file, which was directly sending the clamp value over here. So this is the output file. So the first change we did was instead of sending the instead of getting the minimum value between these two, we directly assign this over there. Over here we also do the same. Instead of getting maximum of between these two, we directly send it. Now instead of so this is the another change we did. So instead of getting the minimum value, we'll get the maximum value now. This is the other change. So instead of again getting the minimum value, we directly send a max TCP window. This is the other change. Again, instead of getting the minimum, we directly send it. So this is the other change over here as well. So instead of doing a write bit shift, we are not doing any bit shift and giving the same value. Now instead of getting the minimum value, we'll directly assign it to the value which is already there. Again, so this is the other change. Again here, instead of getting the minimum value between these two, we directly send the RCV SS thresh. Sorry. Now instead of getting a left bit shift, we directly assign the window to the value which is already assigned to it. Now instead of getting the min value between these two, we will directly send the this one. Now instead of getting the minimum value between the sec size and MSS, we'll directly assign to whatever size is present already over there. Now this is the changes in output. Now coming to timer. Now over here we directly send it the value like this. The other change is we are not giving any if condition over here, and also removing the else condition over here. So basically we are just avoiding this whole condition. Now we are assigning the value of directly assign the value of 5 over here to ICSK backoff, and over here instead of sending the min value, we are directly sending the ISKRTO value, and over here also we are assigning the same value which is also present there. So these are the changes in timer. Then coming to Vino. So this is the first change which we done, is instead of just adding it by 3, we will send both the value over there in the function. And in this, instead of getting the maximum value, we will just directly send the clamp value. And this is the last change we did. Instead of getting the max value, we are directly sending the send CWN value. So these all are from my side. Now Vikram will carry on forward, and then after that Sarvesh will do the video demonstration. Thank you.
Perfect. Hello guys, welcome to my part in the lab 5 video. So Mike might have told you this lab is primarily about you know modifying TCP's parameters. Essentially removing TCP's congestion control algorithm. I mean not congestion control. Sorry, removing TCP's exponential backoff algorithm. Okay, that exponential backoff algorithm is a core part of TCP's AIMD scheme. Okay, so removing that, you basically sort of uh, you're not as humble as normal TCP algorithm, which tries to be extremely disciplined and tries to reduce its congestion rate so much multiplicatively. That's what it means. Additive increase, multiplicative decrease. So it is not so. It's extremely humble and professional in that, in a sense. But it's humble to the effect that it basically punishes itself by reducing its being too, uh, you know, uh, being too humble, being too. It's to the extent of punishing itself, right? Punishing the data rate. So uh, essentially, what uh, one paper researched, a guy called Amit Mondal from Northwestern University, he published a paper about using TCP by removing their exponential backoff algorithm. And you know that removing exponential backoff algorithm is a controversial idea for sure. We'll get to it later why it is controversial. But again, he published a paper about TCP exponential backoff. This paper, let me go to it. Paper. Go to the paper just for no, not this. Exponential backoff from TCP. Mhm. All right. One sec. This one. Yeah. So removing this was a very good paper, highly cited paper, 300 citations. So it's a really good paper. So what he said is, you can basically remove TCP's exponential backoff and still have a relatively good congestion control, as well as a very significant increase in throughput performance. So that's what his core proposal was, and he was able to prove it by simulating in NS2 simulator. He was able to prove it via simulation, obviously, but he was not happy with the current network simulators these days. So he was also proposing that his particular algorithm, his particular algorithm's results on NS2 is not the final say. Yeah, because in reality it might be different. Because the current simulators during the time when he published his paper was not as good. It's not still that great, like as great as mimicking a real networking system. But still, he discussed that in his paper. The current simulators were not that good. So he specifically mentioned on working on simulators that could uh, make possible uh, make possible a simulator that could really mimic real world networks. So uh, so what is the key part of his algorithm? So his key part is basically you have your uh, by removing the exponential backoff algorithm, like you basically readjust your timeout. Okay, the timeout is set to a constant value. That constant value is calculated using an algorithm called Jacobson's algorithm. So you basically set your timeout RTO, your timeout to be just a constant instead of doubling it every time a packet loss has happened, which happens in conventional TCP. So this was his primary chair. This was his very primary post change. Okay, so what is what the argument that he posed is if you basically if your RTO, your timeout, the time it takes for a packet to be in a network, okay, and get out of the network, okay, if it is much greater than RTT, which means you are basically not transmitting multiple copies of the same packet in the network in an active network. So only one packet would be present in the network at a given time, right? So it's a really good, it's a really intuitive thought. So yeah, so this is what he did. So what you're doing is you are waiting till a packet loss has been acknowledged, and you are transmitting the packet, obviously, okay, but you are not transmitting multiple copy. You are not transmitting. You are not being forced into a condition where you are transmitting multiple copies of the packet in the same time. For example, you might have transmitted a packet, and that packet might still be in the network. Might be stuck in a router or something. What a conventional UDP does is it doesn't care. It resends it again. Like in the previous time, when we developed our very own file transfer protocol, when I developed with my friends our very own file transfer protocol, we didn't care about whether there are some existing packets underlying in the network. Okay, so we just blasted it if the packet has not been reached. Whereas what this algorithm does is it will wait, and if the packet loss message has been uh, you know has been acknowledged from the client side, it will wait for that timeout, that constant timeout that we set, and after that it transmits it. Okay, that timeout has been very mathematically calculated. Understanding the network, you definitely have to understand your network in order to calculate that RTO. And once that is done, you set your timeout value. Okay, that timeout value is a constant and carefully calculated, which will ensure that you don't transmit multiple copies. Which will ensure that you are not being forced into a condition where multiple copies of your transmitted packet remains in the link. Okay, so after your packet has been removed from the link, okay, either it has been lost or dropped, you are free to transmit another copy of the packet. That is not a problem because that will not cause congestion. Okay, so one copy of a packet at a time in a current active link is good. Okay, that is his argument. If you set your RTO, your timeout, to be a value, a constant value, not multiplicatively increasing value, as in twice increasing value, as in traditional TCP algorithms. If you do that smartly using Jacobson's algorithm, if you calculate that particular value, it's like 2.45 into RTT. RTT is a return to travel time. Then it is good. You basically you ensure that you don't transmit multiple copies of packets in an active link, which is good. Okay? That is the core mantra, let's say, of this algorithm. So okay, so let's proceed to make the modification. So in this assignment, Mike might have told you, we try to modify the TCP algorithm in such a way that we remove the exponential backoff. To remove exponential backoff, what you have to do is you have to uh, pull a kernel file, from a GitHub repo, from Ubuntu's GitHub repo, because we're using Ubuntu, obviously, and we are making kernel level modifications. Okay, uh, which is basically you go to I'll show you here. So here these are the files, TCP files that we are modifying. So you basically go to, I'm doing it in a AWS instance here. So I actually made the images, so let's come to this later. So you pull that image using GitHub, which Mike might have explained you, and then finally you make modifications. So you make the required modifications, and then finally you build the file. Okay, you build that entire, once this is done, you build that kernel, that modified kernel. That modified kernel contains all these files. Okay, and then you patch this kernel to the AWS instance. Okay, your server and client. Okay, and then you test it out, and this new kernel, this new system has a modified TCP code, and thus without exponential, and then we will see the performance. Right, surveys will demonstrate you the performance of our system. But I just wanted to explain you the other sections of codes that we modify. Okay, especially TCP Hybla, TCP Conk, and in the main file TCP.c, and its associated header file TCP.h. Okay, these require modifications to remove the exponential backoff, and I'm going to explain you drive you through the core concept of what we did, drive you through the steps in what we did, change it, right? Or basically the changes that we did. I'm just going to drive you through the changes that I did. Okay. Yeah. One sec. Okay. So this is the TCP.h file. First we'll go TCP.h file. So going to TCP Hybla. So let me search lab file because I have made the changes. Okay. So what is this? Max window. TCP's window size, sending window size. Okay, buffer. This is a buffer, TCP level buffer. Okay, this is so you are not in application layer anymore. You are in transport layer. Okay, now so in the transport layer you have TCP's buffer. Okay, the amount of space that it can handle, it's in bytes. The amount of bytes that it can hold in the TCP buffer. Okay? And what I did is previously it was 65535U by 2, and what I did is I doubled that uh, window size to 65535U. Okay, doubling the window allows you to handle more packets, basically increasing your throughput by. So that is what we did. So these are some architectural advantage. Architecturally, we are trying to design advantages. Okay, we are trying to tweak some key parameters and get a good throughput. Okay, I'll do. Okay, I'll say the disadvantages of this later, but let's proceed in a linear manner. Okay, first we change this, and then um, one sec. So and then in the second thing, okay, in the second, okay, let me come to this slide. One, two, okay, two, okay. Next, this is the number of duplicate acknowledgements that can be in a current link. Okay, so previously the number of duplicate acknowledgements was 3. Okay, duplicate ACKs just it increases the congestion in a network. Okay, let's face it. Even though ACKs are insignificant, uh, like the packet size is extremely negligible. We can just smile at it. Decreasing it, if you transmit say a 1 GB file, decreasing it definitely has some performance improvement. Okay, so because you're going to transmit so many number of packets. Okay, so decreasing it to 1 is a good idea. And next we go to number of retries. Okay, number of retries, previously it was 6. We decreased it to 5. You can have any value that you want. You can be 4, you can be 3, but again it has a trade-off. There needs to be a balance. If you do retries to be 0, then it means it's just UDP. It's like an UDP system. It will be like it's not in like an UDP system because TCP has some while loop built into it that will keep on retrying. I think so. If you change it to 0, I think it's just like UDP. I think so. So better not mess with it. Better keep it to some rather decreased value rather than just completely decreasing it to 0. You can try it. It's an interesting problem in its own right. Okay. Next we go to the fourth change. The fourth change is one sec. The fourth change. These are the RTO, which are basically the timeout values. Okay? Timeout values. And these timeout values were set according to the paper's proposer. Okay, the author Amit Mondal here proposed some specific uh, values. He advised some specific values, and we tried those values. Okay, 3 by 5, 10, hertz by 10, Hz by 10, all those values. Right. So these are based. He suggested some values and we tried it. So we just tried his values. Okay. So all credits go to Dr. Amit Mondal for this. And then finally, we go to fifth change. And the fifth change, okay, I think the next change. Okay. Okay. We scaled the TCP's window size here. As previously it was 3, and now we changed it to 6. Okay. So increasing the TCP window size, window scaling, you scale the window size, which means it's good for your throughput, right? And then finally, this is the last change. We enabled Naggle. Naggle is an algorithm where let's actually visit Naggle. I searched it. So Naggle's algorithm is a separate TCP optimization that serves a different purpose. Okay, it reduces the number of small packets into the network. Okay, by aggregating them together into a larger packet, which means smaller number of uh, retries, right? No, if a packet is larger, then the probability of losing it is also larger. Yes, that is true. But it reduces the number of transmissions on ACKs, probably, okay, because it's just one packet, a large packet. Okay, so yeah, in some ways it reduces network congestion because sometimes the packet might get through. So it's just a again a link is like a random variable. Okay, you get it sometime and you don't get it. Okay, so a link is always probabilistically modeled. So again, having large packets in some cases work well rather than small packets. So Nagel's algorithm is a very efficiently designed algorithm that works with congestion mitigation, efficiency, uh, or what are all complementary optimization. Okay, and application. And actually, if you remove exponential backoff, Nagel's algorithm kind of helps because uh, it tries to because exponential backoff it means you have no discipline. You literally you don't have any you sort of you rapidly increase your sending rate, right? You're not as disciplined as you're not as humble as your previous TCP count. Okay, so um, combining an Nagel's algorithm with this newly removed exponential TCP sort of is like bringing leveling it down to not as extreme a level, calming it. Okay, and then considering a significant previous overhead, so it does have latency because you're sending large packets. Sometimes they don't get through, and you have to send the entire large packet again. So yeah, there are some disadvantages too. So there are always discussions about it. Okay, so once this is done, okay, so Nagel's feed enabled Nagel's algo, which is good, right? That's it. These are the changes in TCP.h file. Now let's go to TCP Hybla. TCP Hybla is a separate TCP algo. In TCP Hybla, we changed two things, or three. We have emphasized. Okay, okay. We see. Okay. So here we basically changed the congestion window from 2 to 1. We we decreased the congestion window size from 2 to 1, and we also decreased the central congestion. Yeah, we basically decreased the central congestion actually here, and we also decreased the congestion window clamp, which is the maximum value that we can have, from 65,000 to some very low value, 6,250. Be a bit decent about it, okay, for TCP Hybla. And these are the changes in TCP Hybla actually. Anything else? Yeah, we are setting the TCP congestion window to its maximum value, and yeah, that's it. And then let us go to TCP conc. Okay, TCP conc. TCP conc. Uh, okay. So TCP conc, it's the same thing. You are trying to set the sender's congestion window to clamp to its maximum value, right? And you return the maximum congestion value itself. Yeah, instead of choosing a maximum between two values. Okay, you just send the maximum congestion value. These are some architectural changes that needs to that these are some nitty gritty changes that we need to pay careful attention to. I've just followed the paper suggestion because I did not really think through why this uh, like by myself. I did not really read through the entire algo because it's like every code is like 500 to 1,000 lines long in average. So I had just followed his suggestion in the paper. Okay, but yeah, reading this code detailed in through is a really good thing. So I really plan to do this in detail. Okay, in a upcoming video, probably if time allows me to. So let's go to the third change. I also what else? We go to TCP.c. Okay, so in TCP.c, let's go to lab5. Okay. Okay, so here we basically comment out the timeout. What is this? Timeout left shift, timeout left shift equal to 1. It means you're increasing the timeout by 2. This essentially means timeout equal to timeout into 2. Timeout equal to timeout into 2. Okay, and we don't want that. That is what his proposed algorithm was. Amit Mondal proposed that you don't do that. Okay, you just keep a constant value. Okay, so what is that constant value? Uh, I think Mike might have discussed that in his previous thing. It was in another file. It was 2 point something into 2.5 into RTA. So yeah, this is the code where it increases the congestion window twice. Okay, it increases the it increases the timeout twice. Okay, we do not need that. Okay, that is exponential backoff, and this commenting out essentially means we are removing that algorithm, we are removing the strategy. Okay? So we removed it. So that's good. We're removing it in two places. What else? We are setting the TCP's congestion. Previously, it was TCP's central congestion to clamp was set to 0. We don't need that anymore. We just use the default maximum value. It was set to TCP init congestion window. Yeah, TCP was just set to its initial congestion window. We just keep it as it is. Okay, we are not modifying anything. We don't want it to reduce to. This is 0, so we don't need it. So we commented it out. All these increase our performance significantly. If without it, our performance increase would be significant. So yeah, so these are the changes that we made. So in summary, we try to reciprocate uh, Ramit Mondal's proposed changes for removing the exponential backoff algorithm. And to do that, we first need to this is a kernel level change. We first need to pull a custom kernel, a proper Ubuntu kernel, and make our changes. And once we made changes, it transforms into a custom kernel, right? Uh, Strictly speaking. So we then boot our custom kernel. So these are our kernels actually. Okay. So we then boot our kernels to an AMD instance. Sorry, an AWS instance, and it should work. So it will after you compile the kernel, it will generate all these image files, and then you have to patch these image files to your desired system. That's it. So now, what are the advantages of this approach? It increases your throughput. You know, uh, temporarily, not permanently. Temporarily. Why temporarily? Because let's say TCP's exponential algo builders, they are experts, so they won't have an algorithm that is suboptimal. They calculated it for the long run, and they know TCP's exponential algo is the best there is. TCP is not uh, as trivial as UDP. Let's put it bluntly. TCP is a really sophisticated algorithm that has a lot of functionality. Okay, so uh, having these features, they didn't do it for nothing. They have some very big reason, and one of the very big reason is queuing theory. If you send a very long, if you don't have exponential backoff, okay, then every say for example, previously, let's see the advantages first. Okay, say you have a simple network with 9 TCP users and one UDP user. Okay, with TCP's AMD protocol, if there is heavy congestion, okay, if everything is going through a bottleneck, a router, the TCP users will drastically reduce their sending rates. Okay? What happens is they are being very extremely humble, and they reduce their sending rates drastically, so that the congestion will ease the congestion on the bottleneck. Okay, so it is a very moral thing to do. Right? So it is fair for everybody. Whereas the UDP user, he doesn't care. Okay, he literally utilizes all the bandwidth, extra bandwidth that he gets if the TCP users reduce their data rate, reduce their sending rate. Okay, so in this case, a UDP user like very unfairly gets benefits, very unfair benefit, very skewed benefit, very skewed. The distribution would be the distribution data rate distribution would itself be extremely skewed. That it's like it would be like a Pareto. The UDP user would get the maximum. Okay, So this is bad. Okay, so that's why there are several algorithms that the TCP makers optimized. So, particularly in versions like 22, Ubuntu 22, 24, there are so many optimizations that take care of this crucial problem. But uh, removing exponential backoff is a drastic way to get rid of that disadvantage. Okay. So in this case, the TCP algo users would also be sharing equal bandwidth with UDP in this case, even if there is congestion. What is the downside in that? Well, if every user doesn't have the discipline, doesn't have the discipline to slow down themselves if there is congestion, what happens is the router will just basically drop all the packets, and there would be heavy latency, okay, because there would be heavy queuing delay. So what happens is what you lose in your you might have an initial throughput advantage gain, but what you initially gain in the long term you would lose heavily. So you're just basically trading in time. The very initial few time instance, all the users would get extra good throughput, but over the long run their throughput would reduce so drastically because of the long queue that the router has, and its drop tailing. Um Essentially, the overall data rate, average data rate for every user would theoretically drop down to zero. That's it. Or the router might get, due to heavy usage, the router might also have buffer overflow, or have some system level problem. Like it might get heated up. So many issues. So yeah, so this is a very big problem. So that's why removing exponential backoff is a very controversial topic. So we just wanted to show uh, a demonstration of how this is done. Okay, to do this, you have to pull a kernel. Okay, for example, we'll show you CD. We basically let me actually I think it is mentioned in the lab report. But again, the core idea is you pull a GitHub repo, Jammy repo. Because this is Ubuntu 22, so you pull a Jammy repo, and then uh, you first once you pull the repo, you can navigate to that repo. So cd, okay, one sec, ls cd, okay, cd ubuntu, oh, sorry, cd ubuntu, okay, and ls, okay, cd jammy, one sec. Let me see how much time I have. Okay, I have only 2 minutes. Okay, cd jammy, and then cd let ipv4, and you have all these codes now. So there we can modify the codes, and then once you modified it, you have to make your build. Okay, you sudo make -j4. You first have to build a config file, sudo make old config, and then you build your file. Okay, once you just sudo make j4, where j4 is number of processors. Um, so you build your file. Okay, so you use the number of processes to build your file finally, and you get these images. Okay, and then you patch these images to your new system. You install it, you update grub, you specifically go to grub and do these changes, and then the system will have the new kernel, and in the new kernel it will have the updated TCP code. So you test it, and that's it. So this will be showed by Sarvesh. Okay.
Now we'll look into the demonstration part of this video. In this part, we have already created our new kernel, and then the new kernel is installed within our virtual machines. So here we could see that the changed virtual machine version is 5.4.212. Initially, it had 5.4.0.150, and then now we have changed it to this kernel version that we have here. So in this particular lab, we had to download dependencies, and then we had to change our kernel, which used TCP with the exponential backoff algorithm. We have already changed specific folders within the TCP header files and the internal codes of TCP. So after doing that, now we'll check how the file transfer algorithm works for the data that we've created. Yes. So I have already done the file transfer part. I have the outputs here. So for each and every output, I have already configured the router here. So first I have configured the latency and the burst of the message that is being sent. And then I've configured the drop rate as well. So for in this part, we have varied the drop rate, that is from 5% to 10%. And in this part, we have taken, sorry, we haven't dropped the, varied the delay, we have varied the drop rate. Here, we have varied the drop rate to be, we have set the drop rate to be 0, and we have transferred 1 GB file with a 200 ms latency. Yeah. So here we could see whether our client has 200 ms of delay. So in the ping, we find out that we have 200 ms delay. Yeah. So while transferring this, the SCP struggled a lot while having a drop rate around 10%. And it also struggled to transfer data around 20%. So from 10% to 20%, we could see that there is a reduction in the time being taken. This is for 5%, this is for 10% drop rate. Now this is for 0% drop rate. It took very, very less time. And to transfer 1 GB with 0 drop rate, we got around 2.09 minutes. So it's pretty fast. The consistency of the file is checked through the MD5 sum in both of the cases. So in ideal conditions, we obtain around 69 Mbps with this link. We could also improve this link by changing some more intricate variables within the TCP internal files. We have changed only the TCP VNO and the HIBLA part of it for the majority of the project. So yeah, this concludes the demonstration for this lab. We'll see you in the next one. Thank you.